Good morning everybody and welcome to week 2 of online learning. So this week we are going to finish off this chapter. We're going to do stuff on the binomial expansion this week. It will build towards the end of the week. We'll bring partial fractions back in as well. And that should mean that we'll have time for a topic test, I suppose, probably not this week, but first lesson of next week. My intention is to keep going over Easter for two reasons. One, we haven't all of us haven't actually got that much to do probably, but the better reason is in general we're slightly behind where I hoped we would be in terms of the scheme of work, and that's true for pretty much every class, at least with one teacher. And I really don't want us to get too far behind going into year 13, especially as this year we've really struggled to get through the content for a second year running in year 13. If we lose a lot of time now, then we'll struggle probably more next year than we would have done otherwise. So I'm quite keen just to keep going. If anybody has a serious objection to me going on with these videos in the Easter holiday, then obviously I won't keep doing them because it is meant to be your Easter holiday. I will end up setting some papers or something instead, as you would get homework during an Easter holiday. But please let me know if you do totally object, but otherwise if I hear nothing, I will assume everyone's okay with it. So let's get going. So binomial expansion, you guys have come across the binomial expansion before, and just before we get going, hopefully one thing you would have been shown before, and if not, you're about to be shown now, is that in the binomial expansion you get this n choose r coefficient. N choose r also gives you the values in Pascal's triangle, and if you haven't seen what n choose r is in terms of its formula, just been banging it into your calculator, which is quite common, and then it's n factorial over r factorial n minus r factorial. Let me just check myself on that. Yes, that works, doesn't it? If you've forgotten what factorial means, for instance, 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. So n factorial means n times n minus 1 times n minus 2 times n minus 3 times n minus 4 all the way down to 1, all times together. That's the same here. If 6 is n, then that's n minus 1, n minus 2, n minus 3, n minus 4, etc. So we're going to use that a bit this morning. For the first 5 minutes of today, what I'm going to do is show you how, if we use this and we use what you know about the binomial expansion currently, we can take that a step further and show that it actually works for not just whole values of n, but any value of n, which is going to be quite useful, though there is a constraint on the b value. Okay, so you guys have seen the binomial expansion written like this: a plus b all to the power of n, and that's a n. Hello dear, you don't need me, okay. Plus n over 1 factorial, n over 1 factorial, n choose 1, that's much better, a n minus 1 b plus n choose 2 a n minus 2b squared plus n choose 3 a minus 3b cubed, and then it just keeps going on and on and on and on until you get to a point where this becomes b to the n, that becomes a to the 0. That's what you guys have done so far. And what we want to do is just take this a little bit further by sticking this bit in instead and see what happens. So if I stick this formula in instead, this becomes a bit more messy, but let's hopefully I can write it down still. So I'm going to get n factorial over, well, 1 factorial is 1, n minus 1 factorial. So all I'm doing is sticking 1 in here and here. A n minus 1b plus n factorial 2 factorial n minus 2 factorial a n minus 2b squared plus the last one n factorial, well, the last one for now. Hopefully it's a bit obvious later why I keep stopping here and not other places. A n minus 3b cubed plus all of the rest of them. Okay, so what we can do from this point is just try and tidy it up a bit because it's quite messy at the moment. So the first term I can't really tidy up at all, it's just a to the n. This term I can tidy up. This bit on top says n times n minus 1 times n minus 2 times n minus 3 times n minus 4, etc. This is n minus 1 times n minus 2 times n minus 3. If I wrote all of those out, you'll notice that n minus 1 and lowers will have a partner, top and bottom, so they can cancel out. So it would just be left with n lots of a n minus 1b. Similar to this one, the n's and the n minus 2, all the n minus 2's and lower will cancel out, so this will just be left with n minus 1 all over 2 factorial a to the n minus 2b squared. And similarly, this one, these will cancel out mostly to be left with n minus 1, n minus 2 all over 3 factorial a to the n minus 3b cubed, and then it just carries on going. So we've gone from this, which we know and love and can use really well, to something which, well, I'm not sure if it looks necessarily any easier to use. Well, it doesn't look quite as clean, I suppose, but it looks fairly easy to use anyway. If I have certain values of n, I can stick them in here. I can do this quite easily. I could do this in my head instead of using a calculator, which would be quite nice, or writing out Pascal's triangle. Obviously, if I had a big value of n in the middle, this would get a bit messy. However, the key thing is you might be saying, okay, well, how does this link up to that? Because this definitely has a finite amount of terms, whereas this looks like it's just going to keep going. We're going to get a 4 factorial, 5 factorial, 6 factorial. I'm just going to keep getting more and more of these values on top. But if you think about what's happening to the stuff on top, we've got n minus 1, then we've got n minus 1, n minus 2. Eventually, this number at the end, as it keeps growing, and the next one I'm going to have n minus 1, n minus 2, n minus 3. Eventually, that number is going to be as big as n. And when it gets as big as n, that means that the whole term will be 0, because I'll have a 0 in there. And you'll see that every single one of these terms has the stuff from before plus something extra. And then this one's got the n minus 2 extra. The next one will have n minus 3 extra. So once you get to that 0th term, once you get to the term with a 0 in it, all the terms afterwards necessarily will have to be 0. So this does still work, and in fact actually this is just a simplification of the general binomial expansion. This is, well, we know that those zeros are going to turn up, and so we just write it out like this. However, it comes from this in the first place. So we're going to look at this today and say, okay, well, when n's not a whole number, we're going to use this form. However, we're going to just go a little bit further for a minute, because this doesn't work yet for values of n which aren't integers. Okay, this works for values of n's that are integers, but doesn't quite work yet if I had something like n being a half. Okay, so to make this work, first of all, we're gonna do a few different things, but let's just let a equal 1 for starters. if a is 1, then we have 1 plus b to the n, and that's going to be 1 to the n plus n factorial over n minus 1 factorial. I don't need to write the a, do I? Because it's 1 to the power of n. B. What am I doing? Oh, I'm looking at the wrong line. Start again. 1 plus b to the n is equal to, well, 1 to the n is just 1 plus n, 1 to the n minus 1 is 1b, plus nb, plus n minus 1 over 2 factorial b squared, plus n minus 1 n minus 2 3 factorial b cubed plus dot 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 dot. Now this is starting to look really quite clean now, and this is the form it's given to you in your formula booklet. This is known as a general binomial expansion. There are issues, so there are ways of dealing with it if we had something here which isn't 1, but for today's lesson we're just going to assume everything always has 1 there. B is just going to be something, so it could be x, it could be 2x, it could be negative 3x, it could be some amounts of x, whatever you want it to be. Just one note, if you look in your textbook or if you look in the formula sheet, instead of a b here it actually has an x. I'm going to keep writing b's, and the reason for that I will tell you about when we do the second example. I think it causes less confusion if you have a b there. If Miss Hughes disagrees with me, then Miss Hughes is right, just to be clear. So this works, but however it only works in certain scenarios. And the reason why it only works in certain scenarios is if n is, let's say, a half, then this is going to be an infinite sum. And it's going to be an infinite sum because we will never get a value of 0 in the numerator. Hello, Sebastian. Do you want to say hello, Sebastian? There was a, before we went off, someone did say, can they see Sebastian? Sebastian, do you want to say hello? Good, thank you. Oh no, I'm in it. Right, go back to this. So, yeah, so we have an issue if n is not a whole number, because this becomes an infinite sum. And it's an infinite sum, then that's a slight problem, because if I'm adding term after term after term after term, and I'm saying this is actually equal to something, that implies that this right-hand side should actually settle on some value, you know, whatever that value is, 107 or something, whatever. But if you've got an infinite sum, if these keep increasing, then it will never settle on something. So these terms have to be decreasing in some way as we get bigger and bigger, otherwise it will never settle. The only way to make them decrease as these terms get bigger and bigger is to make sure that this value of b gets smaller. Well, this whole thing gets smaller. So if b is less than 1, then as the power gets bigger and bigger and bigger, this gets smaller and smaller and smaller altogether, and so this whole term will never get too big. In fact, it will just get smaller and smaller because this will start tending towards 0 eventually. Try on your calculator. If you put 0.75 into your calculator and raise it to a big power, it gets quite close to 0. If you raise it to an even bigger power, it will get closer to 0, etc., etc. So we have to have that. We have to have that b is actually less than 1, or it could be bigger than minus 1. It has to be within that range. So we say that this is true as long as minus 1, b is greater than minus 1 and less than 1. And if you want to write that in modulus form, you would say that the modulus of b is less than 1. I will always write it like that and then translate it to this, because sometimes it's very useful to do it that way around and helps with your understanding. Okay, so let's just do 2 examples and then I'll leave you guys to do some work for the rest of this lesson. If just a note, if you haven't quite followed what we've done there, I would advise just to watch it back and just see if you can make some sense of it, because it gives you some understanding of where this stuff comes from. However, you do not need to be able to go through this process in your exam and say, and hence this is where it comes from. This is just me trying to link it into something that you've known before. This is the thing that you do need to know. Like I said, it won't have a B on the formula sheet or in your textbook, it'll have X's there. So let's just try 2 examples. And then, like I said, I'll let you get on with some work for the rest of today. So I've got 1 plus x to the negative 3. So I've got 1 plus x to the negative 3. So what I'm going to do is I'm going to write out the formula every time, because I have listened to Miss Hughes. So I've got 1 plus nb plus n minus 1 b squared all over 2 factorial. Doesn't matter really where you put this line. Interesting note, a line like this is called a vinculus. There you go. Didn't think you'd learn that today, did you? N minus 2 b cubed all over 3 factorial. Okay, so I've written down my formula, and I'm writing down my formula because I'm telling the examiner that I know what I'm up to and which form of the binomial expansion I'm going to do. Oh, I should probably add something to the question. I say e.g. The question would say something like expand 1 plus x to the minus 3 up to the x cubed term. So I can write it like this, and you can either then say plus dot 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 on the end. You should really put plus dot 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 on the end if you've got an equal sign there, because otherwise these 2 things wouldn't be equal, just up to there. Or you can say that this is approximately the first few terms. Either way, it doesn't really matter. Sometimes it's easier just to use the approximation. I'm going to change to an approximation now, so I don't have to keep doing that on the end. Okay, so now I can just substitute stuff in. 1 is still 1, plus n's minus 3, and b is x, plus minus 3 minus 1, x squared over 2 factorial. I would suggest that you substitute the n value in and put the minus 1 on there. Yes, you can do it in your head. Yes, it would be so easy to do it. Yes, it's so easy to make a mistake also. It's also good though just to show that you can show the examiner that you know which bit gets subbed into which bit of the formula, because the formula is given. So recognising which formula to use is one thing, but then substituting into it is just another skill you can show. Not a very high level skill, but it's just another thing that you can show the examiner which you can do. And sometimes these things are awarded marks. Okay, so I've written the formula down, I've substituted my values in. I don't need to write that on because I wrote approximations. I can go back to equals now because I had an approximate there, which is equal to. This line is equal to 1 plus minus, that's minus 3x. Minus 3 minus 3 minus 1. Minus 3 minus 1 is minus 4. Times by minus 3 is 12. 12 divided by 2 is 6. I would recommend doing this on your calculator. Don't do it in your head like I am. I just haven't got my calculator to hand. Minus 3 minus 2 is minus 5. Minus 5 times that is 20. That 3 cancels with that 3. Minus 20 divided by 2 is minus 10. Okay, so that's the answer for this one. The question would normally also say state the values that it's what's the word I'm looking for? Valid for. State the values it's valid for, and it would be valid for x being between minus 1 and 1, or in modulus form, x is less than 1. Okay, so it's valid for. Expansion is valid for that. X is less than 1. Okay, so let's just do another example which is slightly more interesting. Yes, Sebastian, I know. I hope you can hear my cat meowing, otherwise it sounds like I'm just talking to no one. So how about expand (1 plus 2x) up to the x cubed term. They could ask you to do it to other terms. Up to the x cubed term normally says that enough, normally tells the examiner that you know how to use the formula sufficiently. Okay, so expand this up to the x cubed term. So the first thing to realise with this one is that 1 plus 2x is equal to 1 plus 2x to the half. And 1 plus 2x to the half, I can use the binomial expansion on this. It's 1 plus nb plus n minus 1b squared over 2 factorial plus n minus 1 n minus 2 b cubed over 3 factorial. Okay, so this is why I use a b and not an x, because if I compare this to what we did earlier now, if I compare it to the actual one, and I literally stick in things like for like, I've got 1 plus b, or 1 plus 2x. So my b term is my 2x, so I'm going to stick a 2x in place of my b's. If you use the formula from the formula sheet or the book, this has got x's here, that's got x's there, and it just looks all a little bit odd, and I don't really care for it very much. It's very clear that you are substituting 2x in for a b here, as opposed to having 2x's here and x's here and everything being a bit strange. So I've got that. I'm not quite sure why I've gone back to equals, but I have. It's up to you when you use approximation signs, etc. So if I substitute stuff in this time, I've got 1 plus half. Now, if you've got things to multiply by each other, I'd make sure you keep them in brackets. Half 2x plus, I've got a half on top, then a half, take away 1, all over 2 factorial. And then I've got 2x squared. If you find yourself in a bit of a pickle here, go on to the next line, but indent it quite heavily. Plus half, half minus 1, half minus 2, 2x cubed, all over 3 factorial. So all I've done is substitute in the halves and substituted in 2x's where the b's are. Okay, so this is all equal to, oh crikey, this is going to be more work this time. So half times 2x, right, I've got that one. That's 1 plus x. Half minus 1 is minus a half times that is minus a quarter, and minus quarter divided by 2 is going to be minus half. Oh no, it's not. It is when I times it by that. Hang on, let me just, yeah, that's fine, yeah, okay. Minus half x squared, so that 4 will cancel with these halves then. Do this on your calculator, please. And the last one, those will cancel. That will be, I think, a half. Yeah. Yes, it will be. Okay. I want someone to check that now. I wish I'd checked it. Okay, so we've got this situation. I think that's absolutely fine. However, we need to still say what it's valid for. So what is it valid for? Well, it's valid for, in general, it's valid for minus 1 is less than b is less than 1. However, in this case, b is 2x. So I substitute it in. Then I divide by 2 to just make it an x, because I always want it in the form x is less than something, or greater than something. So because I've got minus half is less than an x is less than a half, in modulus this just means the same as x is less than a half. If you haven't seen that explicitly written somewhere before, if you've got x is less than some value, let's call it c, then all that means is that this is true. Okay, these two things are equivalent to each other. So once you've got it in this form, you can just say that it's this. This is the more normal way to write it. However, this is perfectly acceptable because they mean the same thing. Okay, what I'd like you guys to do is just basically do some muscle memory type things for the rest of today's lesson. So can you go to exercise 4a and can you do questions 1, 2, 3, and just before you start, if you have something like 1 minus 2x to the half, hopefully you'll notice that is 1 plus minus 2x to the half. That will come in some use if you are struggling with some of the later ones in question 2, I think it is. Okay, so crack through those now, please, guys, and I'll speak to you again tomorrow. Thank you very much. Bye-bye.